All right. So welcome to the fourth lecture. So today, what I'm talking about is Schubert varieties and Kazhdan-Lusztig polynomials. So I want to discuss the theorem that gives the geometric interpretation for Kazhdan-Lusztig polynomials. This is a little bit, well, not just a little bit, it's orders of magnitude more sophisticated than anything I've been discussing so far. In terms of like, you know, if you want to prove some of the statements that I'm discussing today, you need hundreds of pages of maths. Yeah? So I'm again, maybe just remind you of that. The first point that I made, that my goal here is to try to give you some kind of intuition or understanding about something that's very complicated. Okay. So in fitting with today, I found the following quote from Pierre de Lin, who's one of the greatest mathematicians of the 20th century, I would say. He says, "I find the earth and nature so beautiful. I don't like just to go and have a look at a scenery. If you really want to enjoy the view from a mountain, you have to climb it on foot. Similarly, to see nature, you have to walk. As in mathematics, in order to take pleasure in nature, and nature is a beautiful source of pleasure, one has to do some work." Okay. I totally agree with this. And this is particularly fitting for the lecture today. If you really want to understand this, it's like, you know, a year's work or 2 years' work or something like that. Yeah. And also Pierre de Lin invented a lot of the tools that actually prove the stuff that we're discussing today. Okay, so I assume most of you have struggled with the definition of scheme at some point. So you have a rough idea. Some of you know scheme theory rather well. I just want to think today about a scheme as being something which locally looks like the zeros of a set of polynomial equations. So this is a scheme of finite type over C. We won't need to be very technical today. So, you know, if you know what this is, great. Otherwise, you can think that X is something that has a covering such that each UI is a closed subvariety inside some Cn. So if you think about a manifold, what we do is we take Rn and we glue it together to form some interesting global thing. And now what we're doing is saying our interesting thing are zero sets of polynomials. We look at those and then we glue them together to form an interesting global object. Okay. And probably one of an important basic point in mathematical history to be aware of is that I think that people studied manifolds initially because they could. Okay, so if you think about the history of manifold theory, Riemann and Poincaré noticed that the solutions of certain differential equations, for example, locally look like a vector space, or locally look like Rn, and then they started patching them together to form manifolds. But there's many, many situations in mathematical nature where the basic objects are more complicated. They're not manifolds. Okay? And I think that a systematic study of these was not done, not because it's not important, but because it's really hard. And somehow algebraic geometry provides a way of discussing singular spaces in a meaningful way. The other point to make is that singular spaces show up right through representation theory and number theory and algebra. And so it's very important. So every smooth point looks analytically like C to the D, looks locally analytically like C to the D. Okay, so if you think about an elliptic curve or something like that, like the solutions of y squared equals x cubed plus x or something, then this is a complicated space. You can't algebraically parameterize it. You can't algebraically show that it's isomorphic to C, but you can analytically. So holomorphically, it looks like C to the D. Okay. So every smooth point of an algebraic variety looks like any other if they're the same dimension. but every singular point is singular in its own special way. So maybe you know, so there's a famous book called Anna Karenina, and I think the first lines are roughly, every happy family is happy in the same way. Every unhappy family is unhappy in a unique and interesting way. Okay? And this is certainly the case for algebraic varieties. So singular points are kind of singular in their own interesting way. So, and there's this enormous field of singularity theory, which is complicated. Okay, so here's an example of a singularity. It's called Whitney's umbrella. So x squared equals y squared z. So in the exercises, we will try to study this in some detail. But I want to kind of use this. So this is a very useful example to have in mind when understanding the singularities of algebraic varieties. So it's kind of basic example in singularity theory. Has anybody seen Whitney's umbrella before? Some 2 nods. So you could convince, so in the exercises, we study this. So this is, in fact, so basically the way that I think about this is I take a sheet of paper and I kind of cross it over itself in an interesting way. And so the singular locus is where these sheets cross. And so if I look, so here's a, so every smooth point is not interesting. Yeah, it's just every smooth point is the same. But then as you go down this axis, something interesting happens. So if you look at a point here and a neighborhood of it, you get this, it looks like a cross times, so that's what I'm trying to illustrate here. So along the z-axis, a generic point along the z-axis looks like this. And then something very interesting happens at the 0 point. So at the 0 point, this picture is no longer true, and we get something complicated. Okay. Now, can someone guess why this example is kind of interesting? Like, why am I giving you this example? Leonardo is looking like he knows the answer. Maybe, sorry? Yeah, so lots of stuff intersect itself.
It reminds me of one of the examples in Archon, when the parable was when they approach to the z-axis.
Yeah, so it's a really good observation. So if you look at, at z equals 0, so we get x squared equals y squared. And so that's like x squared minus y squared equals 0. So this is x plus y, x minus y equals 0. So it's a cross. And then as you go up, this cross kind of lightens like this. Yeah, that's why I know a way to think about this via its sections. So maybe, does anybody in Hawaii have an idea of why this is an interesting example? Okay, so I will tell you why it's interesting. And get rid of this. So one thing that early singularity theorists thought might be the case is that, so we want to understand singular algebraic varieties by breaking them up into smooth pieces. So we say, here's our Whitney umbrella. So we have the smooth locus, and then we have the singular locus. And we understand, we try to understand what's happening along the singular locus. And on the singular locus, this looks like, most of the time, it looks like a line times a cross. So locally along the singular axis, it looks like we have a kind of normal direction where something interesting is happening, and then the same thing, and then it's just continuing, you know, it's like a product situation locally. But what this Whitney umbrella shows is that you have to be more careful because this product situation might break at some point. So we take the singular locus, which is this z-axis, but there's interesting points of the singular locus. So initially people thought, I'll just take the singular locus and then I'll take the singular locus of the singular locus and then the singular locus of the singular locus of the singular locus. And this will allow me to understand algebraic varieties. But this is too simplistic. And what you need to do is stratify your variety somehow into pieces so that your variety looks like smooth thing times something interesting happening. And this is always possible, but the naive first attempt at doing it would not work. So this would be called the strata. Okay, so we would like to break up our space into pieces which look kind of equally singular. Okay. That's Whitney's umbrella. And this is meant to give you some picture of what singularities of algebraic varieties look like. So basically what happened in the last kind of 40 or 50 years is that people noticed that there's many singular spaces arising naturally in representation theory. And so we need to import techniques from singularity theory in order to understand representation theory. So the archetypal example, which I will not go into anymore in this course, is I think, the most important kind of singular space in geometric representation theory. It's the nilpotent cone. So this is, so n by n traceless matrices, such that all the coefficients of the characteristic polynomial are 0. So this is a fancy way of saying that my matrix is nilpotent. And if I do this for SL2, I get a quadric surface. So this is a picture of a quadric surface. And just in case you're kind of new to algebraic geometry, generally I draw real pictures. So I draw pictures of the real points, but secretly, so there's another beautiful quote by Deline where he says, I don't remember proofs. What I remember is a whole sequence of simple pictures and why they're wrong. Okay? So they're like illustrative pictures of what's going on, but he's also aware of why they're not the real picture of the world. Okay? And I think that's very important. So there's a famous quote of Descartes where he says, geometry is the art of proving correct statements from wrong diagrams. Okay? And he's getting at a similar thing. Okay? So for example, here, this is a picture of the real points of a complex surface. And so, it looks like as you go down the z-axis that something disappears as you go down here, but it's there, it just lives in the complex world. Okay, so there's an enormous array of invariants of singularities. Half of commutative algebra is absorbed with kind of invariants of singularities. We're going to focus on a very kind of soft invariant, like it's topological invariant, called local rational intersection homology. So this is where the spinach begins. Sometimes you have to eat your spinach. So X is an algebraic variety. We can associate to this a fancy looking thing. So I'm just going to try to give you an idea of this. So this is called the bounded derived category of constructible sheaves of Q vector spaces. So let me say very briefly what this is. So I hope you know what a sheaf is. So this is something that assigns vector spaces to open sets in a compatible way. And the most important part of being a sheaf, the kind of non-obvious part of being a sheaf, is the ability to glue. So I can tell whether a section is 0 by looking locally. If it's 0 everywhere, then the thing is 0. And also, if I manage to patch together things on an open cover in a consistent way, then I have a section globally. Now, these are the sheaf axioms. These are the most important things about being a sheaf. Now, basically, if you take the derived category of vector spaces, what one would like this to be roughly is a sheaf with values in the derived category of vector spaces. What one would like this to be is something that assigns to every open set it assigns a complex of vector spaces in the derived category. But it turns out to be hellishly difficult to write down what it means to be a sheaf. So, and now we can actually do this thanks to this new world of infinity categories. But for many years we could not. And so for many years we used a worse definition, which is we take an abelian category of sheaves of vector spaces. We know how, starting with an abelian category, we can build a derived category. We do that. And then we look at a certain full subcategory inside that consisting of things satisfying blah. Okay. But the upshot of all of this is that if I have, so I think that, so Grothendieck really thought about a sheaf as being a kind of measuring stick on your space. And I think that's a good way of thinking about it. So if I have a complex of sheaves, so if I have a sheaf and I plug in an open set, it just spits out a vector space. If I have an object in here, when I put in an open set, it spits out a complex of vector spaces. And these sheaves are such that if I put in an open set, the complex of vector spaces it spits out has finite dimensional cohomology, total cohomology. Yep. So each cohomology group is finite dimensional, and there's finitely many non-zero such groups. Okay. Yeah. So this is what this object is. Yeah. So now there's a very, very important object inside here called the intersection cohomology complex or intersection cohomology sheaf. So often in this world, we abuse notation. We refer to these things as sheaves. Okay, so this is what it's characterized by. So there's this mysterious thing called Verdier duality, which one should think of as being a local version of Poincare duality. So Poincare duality is, some kind of incredibly amazing statement. And what Grothendieck explained to us is that there's a much simpler operation on a vector space, which is taking its dual. And Grothendieck kind of explained to us that we can formulate duality, Poincare duality or something like this, as being the shadow of some kind of interesting local operation, which is Verdier duality. So probably the most important thing to know about Verdier duality is that if I take the constant sheaf on a smooth variety and I shift it so that it sits in the correct degree, then it is Verdier self-dual. Okay, so there's this functor which takes in some complex of sheaves, spits out another complex of sheaves, and this object here is characterized by the fact that it is Verdier self-dual, and also, so that's the first condition, and also its stalks look like the following. So basically, I can look at it. So XD is the strata of dimension D. So I take my space, I break it up into equisingular pieces, like in the Whitney thing. So I might break it up into 3 pieces. I look at the XD as the union of pieces of dimension D. And this intersection cohomology complex has the property that on the open locus, it's just a constant sheaf supported in degree minus D. That's to do with Verdier duality. And then below, it can have rather complicated stalks. Okay. So for example, if I look at on one-dimensional strata, its stalks can go from minus D all the way up to degree minus 1, but they have to be 0 here. So so the kind of key diagonal where you have to have zeros is this diagonal here. Okay, so let's see 2 examples. So here's the intersection cohomology complex on the Whitney umbrella. So here's the Whitney umbrella. I have 3 pieces. I have the smooth locus. I have the z-axis without 0. And then here I have 0. And this sheath, so it's a measuring stick. I can plug in a point. If I plug in a point on the smooth locus, I get q in degree minus 2. If I plug in a point along here, I get q squared in degree minus 2. If I plug in the origin, I get q. So I'm not expecting you to understand why this is the case. I hope to explain why this is the case in a second. I just want to give you a mental picture of what this measuring stick looks like. Here's another example. So this is a 3D quadric cone. This is not the same thing as I was drawing in SL2, even though the picture is identical. So now this is a 3-dimensional quadric cone. Maybe a pop quiz, just to make sure someone's awake. Why am I kind of allowed to draw this funny thing like that? Like this thing doesn't look anything like this equation. What's going on here? Like what would be an equation, like, you know, if you think it back to high school, what would be an equation for this kind of thing? Yeah, exactly. Or x squared plus y squared equals z squared, maybe. Oh, yeah. Yeah, exactly. So the point is, so I don't know, like, you guys didn't do 4 unit, did you? Like, did you have 4? Like we had conic sections when I was in 4 unit, and we had like a lot of fun with hyperbolas and parabolas and ellipses and circles and that kind of stuff. And I was kind of like, you know, there's these weird different worlds. And I remember it totally blew me away when I realized that over the complexes, they just all become the same thing. Yeah, if I move to the complex numbers, then there's no difference between an ellipse and a hyperbola. Yeah, and it's the same thing going on here. So this picture looks like something like x squared plus y squared equals z squared plus, but this is just a quadric. Yeah, and so if I see any quadric equation, I'm allowed to rewrite it in a form where I can draw a pretty picture like this. Yeah. Okay, so I got a bit distracted. So here's the smooth locus. And here's the unique singular point. And this measuring stick, so now it's 3-dimensional, so we expect stuff to occur in degree minus 3 and above. So on this open locus, we get q in degree minus 3. And at this point, we get something interesting. Okay, we get something in degree minus 3 and minus 1.
Does this follow the diagonal rule?
Yeah, because, so that's, thanks heaps for the question. Like, yeah, that's a great question. So let's do it. Let's see why. Oh, thank you. So Bailey for Hawaii, Bailey asked the question, does this follow the diagonal rule? Okay. So in our notation before, this would be x3, and then we'd have x2, x1, and this would be x0, because it's a 0-dimensional stratum. Yeah. And so, you know, these are empty, but if we made some arbitrary stratification to so that they weren't, you'd have q, and then you would have this key 0 here. Then you would have q, and you would have a non-important, like we could potentially have something where that 0 is, but we're not allowed to have something 0 here. And then we have this 0 here. And so that's the diagonal rule in action there. Okay, and the diagonal rule in action up here is this 0 and this 0. Okay. Please ask if something is not making any sense. It's also very useful for me to, you know, I also don't like, it's not meant to make complete sense, but like if it has some kind of semblance of sense, and if something doesn't make sense to you, just let me know. Also, Hawaii, please don't hesitate. We are moving on. So, was someone speaking then? No. Okay, so how does one arrive at these examples? So, imagine that we have a resolution of singularities. So there's a procedure by which we can compute this IC complex only on the space itself. And this is horrendously difficult. So that in a very precise sense, this is the same thing. Remember when I said we're computing Kazhdan-Lusztig polynomials, we start at the identity and we work our way up. And this was the algorithm that we saw that was very beautiful. But then yesterday when making an argument, I said we could also start at the top and work our way down. So starting at the top and working the way down would be this inductive construction of intersection cohomology that is horrendous to carry out in practice. The way that we usually compute intersection cohomology is via resolutions. And this is actually feasible in examples to do this. So we take a resolution. So it's a proper map, X smooth, yeah, I guess I'm assuming that it's a resolution, but that's not so important for here. So there's another object. So this is another object in my derived category, DBC XQ. Now this object is a measuring stick which measures the cohomology of the fibers. So what I mean by that is that so here's my measuring stick. If I take a stalk at a point X, this spits out the cohomology groups of the fibers of my map. Okay, up to a shift. That shift is coming from this shift here. So in this example of the Whitney umbrella, you'll see that there's if you take the normalization map, so the exercise 1 on the exercises today is to write down this normalization map and to realize the Whitney umbrella as being like a folded sheet of C2. So this map, if you look at its fibers over the regular locus, it's a resolution of singularity. So we get 1 point. Along this axis, the fiber is 2 points. And at the singular point, at the most singular point, the fiber is again 1 point. And so when we push it forward, we get exactly this picture. Okay, because we're just taking cohomology of points. Even I can take the cohomology of points. Yeah, I just get a vector space. I just get functions on those points. Okay. And so that's an explanation of where that first computation came from. Here's the explanation of the second, where the second computation came from. So I take this quadric cone, 3-dimensional quadric cone. Now this has a resolution via a vector bundle on P1, which is another. So that might sound fancy. In the exercises, we'll do it very explicitly. So you can. And so the way that I think about this resolution is here I have P1. So I'm drawing it again as a circle, which is the real points. So actually it's a sphere. And I have this vector bundle on it. And what I'm doing is I'm squashing the 0 section of this vector bundle to produce this singular point. Okay, so kind of like taking this thing and going. So over a smooth point, it's a resolution. So I get a point. Over the singular point, I get all of P1 of C, which I've squashed. So I get a 2 sphere. So when I push forward, here I get the cohomology H3 plus I of a point. So I get only something in degree -3. And here I get H3 plus I of P1 of C. So we just compute the cohomology of a 2 sphere, which gives us these 2 groups here. Okay. So in both of these examples, I can explain this computation by writing down. So what happens here is we have this diagonal rule. And if you're lucky enough to find a resolution such that the push forward satisfies this diagonal rule, you've done it. But you cannot always find such a resolution. Okay, so it's not always true that the push forward from a resolution is the IC, but one does have probably my favorite theorem in all of mathematics, the decomposition theorem, which I'm absolutely not doing justice to in this course. but such is life. So if you push forward something from a resolution, so you have a resolution of singularities. If you push forward, you get the thing that you want, what we want, plus lower stuff. And how on earth do we understand that lower stuff? Well, you take a resolution of the lower thing, push forward and get lower stuff again. And then you keep doing that. And then at some point you terminate because you're dropping dimension each time. So, and also like this looks horrendously complicated, but actually you can do it in practice and it's incredibly kind of satisfying and powerful. So maybe, just as an example of how powerful this stuff is, you probably heard that Bao Chao Ngo got a Fields Medal 8 years ago for his proof of the fundamental lemma. So basically what he showed is that for some incredibly interesting maps called the Hitchin fibration, there's no lower stuff in a precise sense. So this allows us to compute this by induction. Okay, so now I just want to explain what this has got to do with flag varieties. So now we come back down to earth a little bit. So Ting's course will be useful. So we take a connected reductive group over C, for example, GLNC. We take a Borel subgroup, for example, upper triangular matrices. And we take a maximal torus contained in the Borel subgroup, for example, diagonal matrices. And that's not a 1 there, that's an asterisk. And we can consider the Weil group. And so this is a Coxeter group once we fixed a Borel subgroup, because then we know what positive roots are and stuff like that. So the flag variety, this all-important object in representation theory, this is probably like of importance on par with the nilpotent cone, the flag variety. So I think Ting discussed this to some extent. So this is a projective variety. And for GLN, we can view it as complete flags. Okay, so I'm told that the reason that these are called flags is we consider the point containing a line, containing a plane. So that looks a little bit like a flag. So if we take for n equals 2 for GLN, then G mod B is just a line inside C2, so it's P1. For n equals 3, this is a line containing a plane in C3. And if you want to do an exercise, there's an exercise, but I didn't put it on the exercise sheet. Let me just give a kind of meta-mathematical remark, which is that my instinct as a PhD student was I always wanted to kind of understand things in these kind of terms. So like, what can I actually get my hands on? And I was very resistant to kind of group theory descriptions of things. Like I didn't like G mod B, I much preferred complete flags. But over time, I've really learned that the group theory descriptions are just so much more powerful. So they kind of distill the essence of the geometry for the stuff that's actually necessary. Like I feel like when you look at this kind of definition, it's very difficult to decide like what's actually an important aspect of the problem and what's just a consequence of your funny particular realization that you're using. Whereas when you think about things group theoretically, I think that you get more payoff. Okay, so these are the important things about G mod B. So G mod B is a projective variety, and in fact, it's the largest projective homogeneous space for G, and that's very important. So, it's incredibly important to know how a group acts, and if your group is an algebraic group, it's incredibly important to know on which spaces does that group act. And the most important kind of fundamental spaces are the homogeneous spaces. So now you can ask, on which homogeneous space does my group act? And as algebraic geometers, we want such a homogeneous space to be projective. And then there's this kind of miracle that there's a largest one, which explains why I think it's so important. So there's this largest projective homogeneous space on which G acts, and this is the flag variety. An enormous amount of kind of stuff about G can be viewed in the flag variety. So G mod B has this decomposition into Schubert cells. So, you know, if you want a kind of analogy of this, just think about like projective space. So projective space is, for example, a point plus a line plus a plane plus, so it's something similar going on here. So here's the geometric meaning of Bruhat order. So if I take this Schubert cell and close it up, I get Schubert cells corresponding exactly to those elements that are less than y in the Bruhat order. So in the simplest example, what is this Bruhat decomposition? This is the decomposition of P1 as being, you know, like often we think about P1 as being C plus a point at infinity. So that point at infinity is one Schubert cell and the rest is the other Schubert cell. And the big one is the one corresponding to S, and indeed its closure contains the identity, and the identity is less than S in Bruhat order. So everything checks out in the first example. So here we have the theorem, which is that, so these Schubert varieties are usually singular. And we can compute this sheaf on the Schubert variety and take its stalk at a point X. So X is code for XB mod B. So this is a point in the flag variety, indexing a stratification. So in this diagram, in the diagrams that I was presenting before, you can imagine that the rows of my diagram are indexed by Weil group elements. And I just want to know what vector spaces are occurring. And what this theorem is telling us is that up to some normalization, these vector spaces are, the Poincare polynomials of these vector spaces are exactly given by Kazhdan-Lusztig polynomials. Okay. So this is nothing like a proof. Okay. It's got no resemblance to a proof. I want to emphasize that. But it's just kind of philosophically correct. Okay. So when we were defining the Kazhdan-Lusztig basis, we had two statements. We had self-duality and we had Bruhat upper triangularity. And when we were defining the ICZ sheaf, we had self-duality, and then some funny vanishing on the diagonal condition. And this vanishing on the diagonal condition is very analogous to the fact that these polynomials are without constant terms. So we think about like this would be the coefficient of V0, this would be the coefficient of V1. Okay. So the fact this vanishing in the diagonal is analogous to the Bruhat upper triangularity. So let me say that this is very much not a proof, but this correspondence is actually bang on. Okay, so this is correct. The dodginess is in this. That's not correct, but it's at least philosophically motivating. And remember our algorithm for computing Kazhdan-Lusztig polynomials was we start off and are you trying to speak Hawaii?
No.
Okay, thank you. So remember when we were computing Kazhdan-Lusztig polynomials, we had this thing where we do this kind of simple operation and then we subtract. So something very analogous happens in the decomposition theorem where we push forward and then we subtract stuff. And this is actually like exactly analogous. So these two are totally justifiable and actually lead to a proof of this statement. Okay. Yeah, so I don't know. I feel like this is a little bit of a banging you over the head lecture. So maybe I'll stop there and you know, please feel free to ask a question if you want. And yep. So tomorrow we will go back to combinatorial invariance land So half of tomorrow will be combinatorial, and then the other half will be more of this geometry. So thank you. So are there any questions from Hawaii?
The stratification, to have intersection cohomology, you need a stratification. Are you stratifying the Schubert variety by these XDs, capital XDs?
So this is
by Schubert cells with length, the same length?
Yeah, so if you wanted to draw that diagram, you would need to take elements with a fixed length D. Yeah.
Right. That would be your XD. Okay.
Yeah, and this is the stratification that I'm using. So like when I was drawing this diagram, it's kind of lumping together strata of the same dimension, even though the intersection cohomology might look different on each of these.
And maybe a silly question, maybe it's got no real meaning, but why is it called intersection cohomology if the stratification is like a disjoint union?
Okay, so that's a great question. So why is this called intersection cohomology? So if you want to be totally inspired about this subject, there's a paper by Kleiman called The Development of Intersection Cohomology Theory, where he goes over the history of this subject. But let me just very briefly explain what went into this. So Goreski and McPherson were very interested in singular spaces. They were some of the first people that said singular spaces are occurring right throughout the mathematical landscape, and we're not taking them seriously. Why is this? And what they are interested in is the failure of Poincare duality. So if you're familiar with Poincare duality from the kind of point of view of intersection theory, basically it says that if I have some cycle that's non-trivial in cohomology, like if you think about a torus and you think about a loop around the torus, Poincare duality is saying that somewhere out there in this space is another cycle which intersects that cycle non-trivially. So like, you know, that cycle, if I try to intersect it with itself, I can move it away from itself and get zero self-intersection. But Poincare duality is telling me that somewhere on that torus, because it closes up, there's another cycle out there that intersects it. It's a totally kind of beautiful and amazing thing. And it's pretty easy to write down singular spaces for which Poincare duality absolutely fails. So firstly, you can imagine that cycles might be stuck in singularities, so you can't move them enough to intersect them well. And secondly, even if you can intersect things, it might not be non-degenerate. And what Goreski and McPherson observed is that the issue in forming these intersections is basically that cycles enter the singular locus too much. And so they started playing around with cohomology groups where you limit the amount to which a cycle can intersect the singularities of your space. And then they computed an insane number of examples. And they also had many discoveries in mathematics that are kind of really deep, they had many different motivations going on. So another motivation was to try to find a spot where characteristic classes of vector bundles live on singular spaces. And anyway, so they had like these partially defined intersection products and everything, and they were calling it intersection cohomology, but there was a whole different range of groups. And at some point, so this is really beautiful in this development of intersection cohomology, I think McPherson ran into a person called Jeff Cheeger. And Jeff Cheeger said, well, if your groups are so good, they should satisfy Poincare duality. And McPherson's like, oh my God, I never thought of that. And he ran home and he looked in his book with Goreski, and they had like all of these examples, all satisfying Poincare duality. Like, oh my God. And then they get to example like 70 and it doesn't. Like, oh. And then they go through example 70 carefully and they realize they'd made a mistake. And so then it was clear they'd found a cohomology theory that satisfies Poincare duality. And it's called intersection cohomology because it's very much based on its genesis is intersection of cycles on a singular space. Yeah. So that's an extended answer to that question, Antoine.
Cool answer.
Question from here. Sorry, you keep going.
So this question may be better suited for tomorrow, but so Ed Richmond has a fairly recent paper giving a complete classification or characterization combinatorially for when two Schubert varieties are isomorphic for potentially different flag varieties. So the question really comes down to with this kind of geometric description of the Kazhdan-Lusztig polynomials, how much information should one expect, if any, that two Schubert varieties from different flag varieties being isomorphic should relate to, nice cases of their Kazhdan-Lusztig polynomials being equal or any kind of combinatorial invariance questions?
Yeah, so that's a good question. So I'll just repeat the question in case everyone didn't get it. So there's recent work on when are two Schubert varieties isomorphic, which is an interesting question. And my understanding of the work is basically that they show that if the integral cohomology rings are isomorphic, then the Schubert varieties are isomorphic, or something along those lines. And so that's already somewhat remarkable. And I would say that it's a pure guess, but I would imagine that the kind of Kazhdan-Lusztig polynomials would give you some kind of approximation of that, but not quite. So it's very important that this is rational. So so this rationality kind of makes more things the same that aren't the same. So maybe I won't. I'll comment on that again tomorrow.
Okay.
Chris? So just for Hawaii, Chris asked, why am I saying that the first arrow is a false proof? The reason is what you would like to say is that somehow Verdier duality is the Kazhdan-Lusztig bar involution. And that's true if you do it incredibly motivically. But if you just do it if you just take Verdier duality and you take Stork's or something naive like that, it absolutely does not work. Okay? So the first arrow can be made into a correct statement, but you need so much baggage that it's no longer a reasonable proof of this theorem, because you've already know way more than way more than you're allowed to know at that point in the argument. Yep. Maybe one thing that I meant to mention at the start of the lecture is that Joel pointed out an issue with something that I said yesterday. So maybe I'll just point and post a note on Slack when I get a chance. The question about what are all edges in the Bruhat graph present in the ordering in Dyer's formula? I said they were and they're not. So if you're interested in that kind of question, I'll post something on Slack about that. Thanks a lot. And also I've been making a big effort to write bigger. So I hope that since some people commented on Monday. So thank you very much.